Happy to have Yin Tat Lee from University of Washington. Is going to tell us about a work in progress, a structured sampling package. Go ahead, please.
Yeah, so this I changed the title a little bit. This talk is basically describing our effort on making software for sampling. This is a genre with my student Wuchi and Santosh. Yeah, we have been working on this for maybe 2 years, and yeah, it's still ongoing. But I guess I can still talk about this. I cannot resist on making these slides. Today is election day, and you probably see a lot of news involved predicting the chance of who is winning. Or maybe for COVID-19, you have seen a lot of news about predicting the future number of patients or something like that. But but how people come up with those charts? So in general, there is one generic way to do this. For example, you can first come up with a model with a bunch of parameters, then you collect a bunch of data. If you use optimization, then you can try to choose the parameter to fit the data the best. But then if you use optimization, you will just get one outcome. But often you want to know the probability of certain outcome. Then in that case, you can, for example, use Bayes' theorem to get you a formula for each parameter, what is the probability that will happen. And you can think sampling is a basic tool to predict with uncertainty. And this is especially useful for this year. And in this talk, I will focus on in this talk, I will focus on this problem. You want to sample from exponential negative f, where f is convex. By the way, if you have any question, feel free to stop me. I only have 20 slides, so there should be plenty of time for questions. Throughout the talk, n is the number of variables. So when you want to come up with a software to do sampling, then the first thing you will ask is how the f is given. If you went to the talk I gave 2 weeks ago, maybe, in that talk, I will focus on the regime f is given by oracle. Given the x, you can compute the value fx. This topic is very well studied in TCS, and those algorithms is in fact very good. They are efficient and very robust, especially for low dimension case. For example, you have this table of running time. People are making improvement year after year. But unfortunately, there is some belief there should be some informatic lower bound of this problem. No one knows what is the informatic lower bound, but we believe there should be a lower bound. At least you can prove omega n, but probably it is worse than that. And currently, the best is n cube assuming KLS conjecture. But even for n iteration, it will be too bad for practice, because if you have a million parameter, then you need a million steps that will take forever in practice. So in practice, people more focus on this regime. You assume you can assess not just f, you can also assess the gradient of f. Then you come up with some algo to solve this. And in this talk, I will focus on another regime I call structure model. Namely, f is of a certain form, and the problem is given explicitly. For example, if f is a quadratic function, then you can just given the matrix directly. Then you will not get any informatic lower bound. So in principle, you have more information, you should expect your algo is faster. One thing to highlight is both problem is very well studied in convex optimization. The reason we assume f is convex is beyond this case, we don't have too much theoretical guarantee on this problem. And also you should notice sampling is a problem more general than optimization. For example, if you want to minimize f, then what you do, if someone gives you an oracle to sample, then you can just sample from e to negative a million, maybe some large number fx. if you are able to sample from this guy, then the solution X will be a good approximation of the minimizer. So you should think implicitly inside all sampling algo, there is an optimization algo hidden inside. So to understand what's happening, is good to study the optimization case first. In optimization, there is also study on this problem in these two different regimes. Again, for the first order regime, we're given f, you can only access the function f by f and gradient f. And there is many different algo, for example, gradient descent. And there is many package based on those algo. For example, we use TensorFlow. And in general, the performance of those algo depends on if the problem is well conditioned. Namely, if you draw the level set of the function, if the level set look very skewed, then those are they are bad conditioning. And if the level set look like a sphere, then we call that well conditioned. And for first order method, they are usually faster for those sphere shape. And for optimization, people also study the structure model. For example, one particular model people study is this. You optimize a linear function over linear constraint with an inequality constraint. Those are linear programs. And example algo is integral method, and there's many packages on this. And in general, the performance depends on if the matrix A have certain sparsity pattern. So this depends on where is the non-zero of A happens instead of the numerical number of A. So these two is quite different when they're good. What I want to argue is, even though nowadays people is very focused on deep learning, so all the software is really based on first order, but I still want to highlight both method is important even for nowadays. Let me just give you a classical example showcase why first order method is limited for some problem. All the first order method look like this. You first compute gradient at certain point, and then you move the current point according to gradient using some formula. But those methods will be very slow for example, this problem. This is a very basic problem. The problem is just sum of difference of square. And let's say you know the first point is 0, this is 1. And you try to use some gradient method to solve it. Then you start with the initial solution. Let's say you start with something like this. Then one thing you notice is when you compute the gradient, the first step, the only non-zero in the gradient will be this. All other coordinate, because all the label is 0, if you compute the gradient, the gradient at this point will be 0. So naturally, if you move according to gradient, this shouldn't move because you don't see that coordinate at all. So you can see if you run any first order method, essentially the information is propagate coordinate by coordinate. So for this problem, you should expect you need n steps to solve it. And in general, first order method is slow if your problem have large diameter. Diameter in the sense how the information can propagate through the gradient. In fact, I have done a funny experiment. Let's say n is 100,000, and I use a good GPU to solve it. Using TensorFlow, it will take 1 hour. But if you just give this problem to MATLAB, it will solve it in 0.1 second, even for a 10 years old CPU. So yeah, for some problem, first order method is quite limited. Now I will switch to the sampling case. For sampling case, similarly, you can characterize algorithm into these two cases. For first order, in optimization, you have gradient descent, and for sampling, you have Lagrangian dynamic. And essentially, you can think it's just gradient descent, but each step you add some noise to make sure you are doing sampling. And similarly, you have package based on those algo. There is many package on this, and similarly, the performance depends on if the problem is well conditioned. You can ask the similar question for structured problem, and similarly, you can define some problem look like linear program. You sample from exponential distribution over some linear constraint and inequality constraint. And yeah, and also you have algo similar to intuitive pond. That is again just running intuitive pond plus noise. The only difference is there is maybe 10 of thousands of paper on intuitive pond, but maybe there is less than 10 paper on this sampling case. So there is much less literature on this. And you should expect the performance depends on the sparsity. For people doing TCS, you can think those algo give you polynomial time, namely the running time only depends on the input size. But those algo in general is pseudo polynomial time. The running time depends on the numerical number in the input. And yeah, basically there is almost no paper on this, and naturally there is no package. So apparently this could be a startup idea. You can write a package on this. So this is what we are trying to do. Yeah, we have been doing this for 2 years, and yeah, the result is promising, but we realize there is a lot of, because there is not too much research, we realize there is a lot of research we need to done in order to get the algo right. But let me first explain why people care about this problem. Certainly, you need people solve this problem before you write any program. Turns out this problem has many applications. Let me just give you one in biology. Let's say you consider the vector V. Each coordinate represents one chemical reaction in your body. Then certainly chemical reaction satisfies some mass conservation law. So it will satisfy some equality. Also, certainly reaction should be larger than 0, so it also satisfies some inequality. So essentially, you can think we live in some particle, and turns out you can find out the description of this particle by reading the DNA. So one way some system biology simulate your body is to sample from an exponential distribution over a particle. Yeah, this picture is some picture from Wikipedia showcase how each chemical in your body and how they react. And in reality, the picture look more like this. In your body, there's many chemical, and there is a lot of people using this to do a lot of different experiment on your body, but in a computer. So this is one application. Now let me give you more ML application. As you probably seen, logistic model and Lasso is a popular model in ML. One thing to notice is both model. For example, this model, you notice this is a scalar, and then this is just a scalar function. So for both model, you can write it actually in this way. F is just sum of scalar function, but the thing inside is some linear function. And one basic way to learn the model is to sample from e to negative f. This is how statisticians do. But how you formulate this problem into this linear program form? Do you see it? Turns out what you can do is you can set Si is AI transpose X. If you do this, then you can write it into a linear matrix form AX equals to S. Then now our goal is to sample from e to negative Fi Si. subject to this constraint. Now to make this linear, you can create an extra variable y. You restrict y larger than FISI. Then you can prove this distribution is exactly the same as sampling from E to negative f. So this is not exactly inequality constraint. Notice you have some f here. If there is no f here, then this is exactly the linear programs. But essentially, you can think we're restricting the inequality constraint by a two-dimension convex set. The convex set is S, y, where y larger than f. Yeah, I'm using mouse to draw, that's why I can hardly write. And all the algo for the LP case is easy to extend to this case because you're just changing a one-dimension point to convert that to 2. Currently, our software can only handle this case because we haven't nailed down the algorithm for LP yet. Let me just try to highlight why sampling is particularly difficult for making a package. Given PyTorch can solve all optimization problems, why we expect PyTorch Pro cannot do that. So this is a quiz. Maybe some audience can give me an answer. How long does it take for sunlight to reach Earth? This is related to sampling. So anyone can give an answer.
Like 8 minutes?
The answer is, no matter what you say, I will say it's 1. It is 8 minutes from the surface to Earth, but from center to the Earth, it takes 100,000 years. Anyone know why? The reason is this, at the center of the sun, the light particle is basically moving like a Brownian motion because the density is too high. So it is doing Brownian motion, although the distance from the center to the surface is much shorter, but because it is doing Brownian motion, it will take forever. Yeah, you can Google it, those are real. I see some people really puzzle about this, but anyway. But you can look at the cartoon. If you are Mr. Bean, you go from 0 to n. If you want a straight line, then you take n unit of time. But if you are drunk, you will take n square of time. And that's why you have this huge discrepancy. Similarly, for optimization, it is known if your problem have condition number k. In this talk, it's not important to define this, but some measurement of how difficult the problem is. Then optimization can do it in square carpet step. For sampling, people believe carpet probably is the best you can do. By the way, this is still an open problem. People are still making progress, and we still don't get the answer yet. But in general, you can imagine sampling is like square the running time of optimization because of this sampling behavior. This is not a lower bound. This analogy could be totally wrong. Maybe there is some smart algo of doing sampling beyond just doing Brownian motion. But one takeaway is I want to say a bad algo with a GPU could be a good algo for optimization, but a bad algo with a GPU for sampling could still be a bad algo because it's just too bad. Here is another reason sampling is difficult. For optimization, we can take a very large step size. For example, let's say gradient descent. In general, you can take a step size like 1 over Lipschitz constant of the gradient. Turns out for sampling, it is more complicated. First of all, the algorithm need to be changed a little bit. Each step you move according to gradient, but you need to add the noise such that you explore the space. And then you need to do a step to ensure the stationary distribution is correct. This is not important to this talk, But turns out what happens is you can prove you need to take step size like 1/n times the Lipschitz gradient. And if you take anything larger than then this step will never accept any probability. So this is quite horrible. Yeah, so in general, sampling need to take smaller step, and because this is randomizing small step, the effect will be even worse because you're squaring that step size. And now we switch to why I believe in-2-point will be a very good sampling algo. I'm not going to really teach what is in-2-point, so I will just draw a picture. Let's say you are solving a linear program. You can think in-2-point method is like putting a positive charge on every boundary and also at your current point. And then you release the point, and then let's say you optimize over this direction, then you go out according to the gravity with the charge. And what important is in practice, usually it takes less than 30 steps, or maybe it usually takes not many steps according to the dimension. And for sampling, you can define a similar algorithm. Instead of going to a certain direction, it's more like doing random motion per some force field, under some force field. And if what our analogy about sampling is right, if the sampling algo takes square number of steps in the optimization case, then it just has 1,000 steps is not too bad. Precisely what our package implement is this algo. We do a Riemann homotheneum and Monte Carlo method with metric given by Hessian of some log barrier. There's too many terms here, so let me explain it carefully by a picture. I think now everyone understands what this algo is doing. I will explain few slides later. But I will first give you some experiment. So this is some preliminary result. This package is in GitHub. Currently is implement using MATLAB. I know people use Python this day, but we're still experimenting. The algo will transition to other language later. So let me test it with some. Oh, by the way, every example I pick is handpicked such that other algo is really bad and our algo is really good. I'm very honest about this. But here is a very handpicked example. Imagine you have a sequence of X. Your model is this. Every variable is generated by the previous variable plus a Gaussian scalar. And then we observe the data x1 is 0, xd is 0. When we say I pick this is because this, if you write it carefully, it turns out the distribution of x just follows a multivariable Gaussian distribution. So all the commercial software can solve this without changing the algo. So it's convenient. Here is a picture of one sample look like. This is the k and this is xk. Because of the observation, this is 0, this is 0. And the sample is look like a Brownian bridge except I scale them appropriately. So here is a plot of our algo versus some other commercial software. A student told me NumPy is one of the best commercial software currently. So you can see our algo is slightly better than them. You see we will improve the running time from 4 to 1.4. I mean the exponent. I suspect if there is still many details of the algo can be nailed down. I believe one day we can make it to more like x instead of x to some other exponent. And the curve should be even lower. Yeah, but we are still implementing. For example, if we transition to C, then at least the running time will improve by a few factors. But one thing I want to point out is you can think this is just a very simple time series model. There is many statistic model involve a time series. But even for that simple time series model, if your dimension is large, existing software cannot really handle it well if they are yield conditioning. The reason I pick 1/k here is to make the problem yield conditioning. If they are constant, then the existing software will look more like, I guess it will look more like this. It look more like x squared instead of x to the 4. But if it is yield condition look like this, then they simply cannot solve. So this is more artificial example. So let me switch to a more realistic example.
Hold on, Yin Tat. So I'm kind of missing the context here, because you were talking about this, Riemannian, Lagrangian, Hessian, whatever sampler. Is that the? I mean, that's usually good for polytopes. There's no there's only 2 linear constraints here.
Yeah, there is no polytope here. There is a linear. Okay, what happens is at this problem, you define s equals to xk minus xk.
I see. Then under this change of variables, this is a polytope. Gotcha.
This is not precisely polytope, but it is sampling exponential distribution.
I mean, it's a bunch of linear constraints.
Yeah.
Got it.
Yeah, in general, a lot of problems, although they don't look like polytope, you can transform it in that way. Yeah.
And this you ran like this Hamiltonian whatever algorithm.
Yeah, we run that.
Yeah. Okay.
Yeah, we essentially, it's just you download the package and run it. Yeah, so the another example we test is this one. This is how we start the project, and it will give us a model of some of human. So 3 years ago, Roland gave us a very large model of human, and they have a lot of chemical and reaction. And they asked us a question how to sample from this polytope. The reason they asked this is, the matrix look like this. I draw it here. The reason they asked us is because if they use their current software, their software is based on something like KM1. It's a zero order method. Roughly speaking, their software need 1 century to get 1 sample. So you shouldn't use it. If you try to use any other commercial software, those algos simply cannot move because the step size need to be like 10 to the -7. And then, again, maybe you need a million years to solve this problem. That's why we start working on this project. Currently, our software need 1 hour to get 1 sample. The reason, I suspect the reason why current software have real difficulty of this is, imagine in your body, each chemical reaction, they happens in the rate that is very different. For example, oxygen may do a lot of reaction, but some other obscure chemical the rate may be way smaller. So this problem in some sense is very ill conditioned, and that's why existing software simply cannot run. Another benefit of our software is very robust. For example, there is a famous data set on polytope is lib. Our software can sample according to inside any of those polytope. But if you use existing software, they probably can only handle maybe few % of the data set instead of all. So this is very robust. So now I guess this is more TCS talk, so I should talk about what is exactly the algo. So our algo is, I need to first explain what is homotonic Monte Carlo first. I should highlight all the commercial software based on this. We are doing similarly. So the idea is this. In general, the difficulty of designing MCMC for sampling is you need to make sure the distribution is preserved for each step. And in order to preserve the distribution, we need to do a filtering. And usually the filtering forces us to take very small step size. And there is a very nice HMC. They extend the POM into one extra set of variable V. You can think V is the velocity. Instead of sample from E to negative F, you sample from E to negative F plus log of V. Notice if you can sample from this, you can get a sample from X by ignoring the variable V. So this is just the same POM. The beautiful about this is the algo. You can think the algo is like this. I am drawing XSS and VSS here. In general, you have many variables here. In general, this is n different dimension here and different dimension here. So you can think we have the distribution. I'm drawing the level set of the distribution. So what the algo do is each step you conditional on your X and you draw the distribution on the direction V. This is very simple because fixing X sample from V is just a Gaussian distribution. So this step is very fast. Now the key thing the algo is doing is, let's say you draw the points here. Now what the algo is doing is it trying to do a rotation in the space. The rotation will preserve the distribution. In particular, it will do a mapping from XV to TXV. For example, this is XV. Then the new point here is TXV. And what happens is this map will maintain the H value. Yeah, it will move along the level set. And also it will preserve the volume element. Say you have some picture here, after you move, then you will move to some other. If you apply the map from this element, then you will move to another element with the same volume. So this map preserves the density. And this map is defined by ODE like this. This is the Hamiltonian dynamic. And you can prove if you solve this ODE and move to time equals to 1, so you start at XV, you solve this ODE to move, and then you stop at certain time, you can prove this map will preserve the density of the distribution. So this is the algo. Each step you fix X and sample according to V, then you solve an ODE to rotate along the space, and then you repeat. And the beautiful about this algo is if you solve the ODE exactly, you don't need to do the filtering step. You can prove the algo preserves the density. So you can take a really, really large step size. The algo will still be correct. And also we know how to solve ODE efficiently. That's why this is a very good algo. But this algo is slow when the distribution is not well conditioned. If the distribution is this, turns out this algo is still slow. You can think the previous algo is picking V according to a standard Gaussian distribution. And roughly speaking, it will move along the direction V. What we do is we sample from a non-static Gaussian instead. Then the algo will look like this. The H function, the formula changed because you want to sample from a non-Gaussian. You can check this formula if you restrict on V. If you fix X, then the distribution on V is just a Gaussian distribution according to a matrix G. And in general, we'll pick different G for each different point. So this is the Riemann HMC. The algo is exactly the same, except we're changing the formula of H. And turns out if you compute the derivative of H, it just involves solving some linear system. So this algo is still easy to implement. It just involves solving some linear system. And remember, our problem have some constraint. We have some AX equals to B constraint. So you need to pick your metric on that subspace, and yeah, you define things carefully such that the MC always preserve the constraint. Then turns out what you do is you just replace the inverse by pseudo inverse and determinant by pseudo determinant. Again, the algorithm is exactly the same, except I change the formula H again. But now if you compute the derivative of H, it will involve pseudo determinant. You can do that by SVD. This is lower. But what is the metric we pick? If, for example, if the constraint is X larger than 0, you can think, let's say the problem is X is here. You want to pick the metric such that the distance from any point to any other point is kind of small. Then one natural choice of metric is the point kind metric. Every point to the other point have distance roughly the same up to a log term. If you pick this metric and then substitute to the previous formula, you can simplify the equation a little bit and get some explicit formula. Now the formula doesn't involve pseudo determinant. So now all pseudoless is gone and there's no SVD is needed. And also you can prove this algo is invariant under many transformations. For example, I remember if you multiply A by, remember you have a constraint AX equals to B. I think if you multiply both sides by some matrix, the algo will be still the same. Or if you scale X by some scalar, it will be still the same. And in general, you can prove this algo take polynomial time. So it is independent
but in that, if you duplicate the same constraint,
yeah,
you take
then
two copies, then it's not.
Yeah,
right?
And turns out in practice we found some polytope. We are very slow and we are still trying to fix it. There is some way to handle that, but usually those ways is very expensive to implement in practice. That's why we are still trying to look for a better way to handle that issue. Yeah,
it's
but
like in general, you could like assign a weight to each constraint, kind of like how much this constraint matters.
Yeah, we are trying to do that, but we're still struggling on how to make that practical. Yeah, by the way, just to remind you in general how you solve linear system. In practice, matrix is usually sparse. Say this is the matrix you want to solve. I call this is M. Oh, I saw some chat. How this issue is dealt with. Oh, someone asked for the duplication of constraint is how people handle this issue in LP in practice. And somehow in practice, they don't have this issue. That's why I still understanding why it happens in sampling, but not LP. Yeah, let's say you have a matrix M, and in general, people solve the linear system by doing a Charles-Heath imposition. Those are triangle matrix. And if you represent your matrix by triangle, then it's easy to solve a triangle. M inverse is just you just solve two triangle system. So the difficulty is how you do this decomposition. If you do it naively, usually you get a dense matrix, so the running time is horrible. But turns out in practice, usually you can reorder the variable in certain ways such that the Charles-Heath imposition is sparse. And here, this is some example, those let me point out if you do Charles, here is the running time. Honestly, I'm really stunned by this example. I, in general, don't believe this Excel curve fitting. So this curve here, this is the problem size in terms of number of non-zero. This is the running time. I'm using nanosecond. You can see what is the running time. According to Excel, seems the running time is very close to linear. Yeah, but I remember when I was undergrad, I was doing scientific computing, and people in that area like to say it is very difficult to beat MATLAB for solving linear system. Even I define a very smart algo for my particular problem. Yeah, and they also like to say, yeah, the running time is quite close to linear in practice. And so solving linear system is really not a problem for us. Also, if you look carefully in our Hamiltonian formula, there is a lot determinant. Turns out you can compute gradient of lot determinant by taking auto differentiation on the Cholesky algo. So you can still do it very efficiently. Yeah, and that is what we do in the algo. The real difficulty is just to implement it. We expect there should be roughly 100 times improvement is possible on this problem. The first thing we want to fix later is exactly what Roland said. It turns out there is some polytope, there is many redundant constraints, and our metric is not ideal for those polytope. And yeah, we still haven't figured out what is the barrier, where is the metric that is easy to compute and is faster. Another thing we want to study is how to solve the linear system faster. Certainly is the reason is this problem is quite special. We are solving the linear system again and again, just the numerical value change, but the sparsity pattern is same for all the linear system inside the algo. So maybe we can take advantage of them and get a better linear system solver. Currently, we are doing a very naive ODE solver. We are just using an implicit. Currently, our algo is based on implicit Euler. This is basically the most naive algo out there. So we believe there should be a better algo we can use. And this is probably why in our experiment, the running time is n to the 1.4 instead of 1. We know if you use this algo, you cannot get linear. You need higher order ODE solver. And yeah, certainly in order people to use, we need to generalize beyond polytope. And then the problem become more and more system-ish. There is many parameters we should auto-tune. We didn't implement the algo correctly according to the CPU architecture. There is for example, we didn't use multi-core. We didn't use GPU, and we didn't use very complicated compiler technique. So we believe our algo should be way faster. Although our algo is already super fast currently, but yeah, but we are still trying to make sure our algo is robust and fast. And in general, we believe your sampling should be, you can make, my general belief is you can solve you can sample maybe as fast as 10 times of the cost of solving a linear programs. And we're still quite far away from that goal. Yeah, but honestly, my vision is not implementing all of those. If you think about all the commercial software, they have a huge company behind them. For example, the one we compare against that is done by Uber, and TensorFlow is done by Google. And certainly, I don't want to spend 100 years on this project. And my really hope is some statistician or some practitioner can pick up from this project instead of I try to convince them. Yeah, that's it. Any questions?
Yeah, Nike?
Yeah, I have a question. Where did the Hessian show up?
Hessian? Oh, you mean where is? Oh, what do you mean by Hessian?
I think at some point you mentioned.
Oh, Hessian. Okay, sure. More precisely, for this constraint, we use the metric is Poincare metric. But for a more general convex set, we use the metric given by Hessian of some function.
What is phi?
Let's say your polytope is this thing. Then we define a function phi such that it blow up on the boundary. Then we use the Hessian of that function.
I see.
Yeah.
Are there other questions?
So if it blows up really close to the boundary, only really close, then practically what you do is just billiard, like the Hamiltonian flow is just billiard.
Yeah,
do you know if are there some like nice conditions on the polytope for which billiard is effectively as good as what you're doing? Like, I don't know, suppose it's like isotropic or
yeah, the trouble is this, for my algo, you can put, let's say for a hypercube, the running time will just involve polylog step. But for billiard, I think you will essentially to touch the constraint n times at least. I don't know what is the lower bound for billiard for hypercube.
Probably for hypercube, it's pretty good, right? I mean,
but at least you should expect you should take n step. I don't know.
Yeah.
Yeah, then n step is already difficult to implement. Yeah, for example, in my experiment here, although I didn't write down the number of iterations for our algo, we take 20 to 40 iterations per sample, even for very large dimension. Yeah, so that's,
And I guess one more question. So, I mean, this only makes sense if like the density is the indicator of some polytopes times e to the like an x linear, like a log linear function. But if your function is, you know, log concave and not log linear, but you know, maybe not like two log concave. Maybe let's just say piecewise log linear and log concave. Can you still do something by using
usually you can by introducing new variable to write into a form that look more like this. Usually you can write down into a form x is given by product of small dimension comma set.
Sorry, can you repeat that?
Usually you can, for example, these two problems, they have nothing related to polytope. But by introducing some new variable, then it becomes a polytope-ish.
Right.
Yeah. And usually you can do that for many problems.
Yeah, but I'm not asking about the polytope. I'm asking about, you know, you want to end up with a log linear potential in this polytope.
Yeah, but for example, this problem, originally the density is not linear. We formulate to a linear.
Yeah. In this case, because it's two-dimensional, then you can easily like approximate it by. I agree, but I mean, I'm just asking, you know, I mean, I agree that this captures a lot of cases already.
Oh yeah, but in general, then you can do self-concordance barrier. I mean, technically, sampling from this is same as sampling from a comma set.
Sure. Yeah. So you just look at levels. I agree. Yeah.
But
so
then
if F is nice, you can just look at level sets of F.
Yeah, I know one horrible barrier people use is just log F. If you have, let's say for the set F larger than 0. One barrier people use in practice is just log F. It will not be self-concordance, but sometimes it still work. Yeah, I don't know for this sampling whether it will work if I just do that.
Cool, thanks.
Okay, any additional questions or comments? If not, let's thank Yin Tat Lee for a nice talk.
See you.